In our last lesson, we learned that finding the area between a function and the x-axis gives us the change over time when our function is a rate of change. And we started approximating area using rectangles, which you probably noticed were pretty bulky. A lot of the times they went over the function, sometimes they went under the function, and they didn't give us a great approximation. So mathematicians quickly realized there was a more efficient shape to use, and that is a trapezoid. So our learning target today is to continue approximating area under a curve, but to learn how to do so using the trapezoidal approximation method, or just TRAP. So the reason that trapezoids provide a better approximation than left or right rectangles is because they fit closer to the function. So if you look at the graphic we have here, the sides of the trapezoids are still parallel like a rectangle, but the top of the trapezoid is slanted, and that does a much better job of fitting closer to an increasing or a decreasing function. What's interesting is that trapezoidal approximation is actually equal to the numerical average of your left and right rectangular approximation. And I'd like to show you why this is just by looking at the formula for the area of a trapezoid. You might not have it memorized, but hopefully it looks familiar. It's 1/2 times the height of the trapezoid, which again is on the x-axis, times the sum of the bases. So for this first trapezoid, you would have base 1 and base 2, and the bases are always parallel. So that's why when we started with rectangles, we put our heights on the bottom, because I knew moving forward our bases would be our y values on these trapezoids. So anyways, if you look at that formula, I want to think about distributing that 1/2 to both of our bases. When you do that and rewrite it, the 2 ends up in the denominator from the 1/2. The height gets multiplied by b1 and b2, and they're added together. So when we have that expression, let's look at this b1h. If we relate it to the graphic we have here, that is the same as if you did a left rectangular approximation. So your b1 would be your base for your left rectangle, and your h would be your height. And then if it was shifted over to the right, that would give us this b2h area. So if you substitute those expressions in, we've got our formula for the trapezoidal approximation, which is your left and right RAM added together and then just divided by 2. And that's why we say it's the average between the two. So the good news for us is that we have learned how to do left and right RAM, and so it's going to allow us to continue to practice those skills, and then just to add them together, divide by 2, and also get a trapezoidal approximation. So before we look at our first example, let's talk about that issue of over and underestimate, because you will be asked about that for trapezoidal approximations as well. And with rectangular, you might remember it all depended on whether the function was increasing or decreasing. For trapezoidal, the concept actually changes a little bit. It's the concavity that determines whether the approximation is less than or greater than the actual value. So let's look at that. We'll use this graph that we're looking at. You can see that the graph is concave up. So I'm going to just draw a little sample here to the side. When you fit a trapezoid on a concave up graph, you start with the 2 endpoints. You kind of draw the bases down from that, and then when you connect that top piece, you can see your trapezoid goes over the original concave up function. So that's going to be an overestimate when it's concave up. So just to show you, the opposite is true. If you start with a function that's concave down and you connect those endpoints and put a trapezoid underneath, you can see that the trapezoid stays under the function when the function is concave down. So it's really important to realize those relationships as opposed to the relationships for rectangular approximation method. And we'll practice them so we'll get comfortable. I just realized I forgot my R, and you probably did too. So fill that in, and then we'll look at that first example. So just like when we saw rectangular approximation for the first time, I think it's important to have a visual to relate your first example to. so you can think about what's going on. This actually is the same function we used on our last lesson. It's x squared plus 1, that parabola, and we have an interval from 0 to 3. We're going to estimate the area using trapezoidal with 3 subintervals, so they're telling us to use 3 trapezoids of equal length. So I know I can divide my interval up into 3 equal lengths to find my height. So we're actually going to use that same height formula that we learned for rectangular. So that's your difference in your interval, so 3 minus 0 over 3, because we're dividing by how many trapezoids we want. And that gives us a height of 1, and we can confirm that pretty easily with our visual graphic. The next thing we need to do is come up with a table of x and y values based on our function and our interval, using that height number to distinguish the increments of our x. So we're going to start at 0, and since my height is 1 of all my equal subintervals, I'm going to jump by 1s until I get to the end of my interval, which is 3. And then of course we know whenever we have an x value, we can find y by plugging it into the original function. So double check, but I have 1, 2, 5, and 10 for those values. We learned in the introduction that the trapezoidal approximation is equal to the average of the left and right RAM. So we're going to set that thought up, and actually it took me a minute to write this out, so you might want to pause it as well. But I set up a bracket for my left RAM, so I know I have 3 subintervals that we're using for left, and then the same 3 subintervals we're using for right. Added together, all divided by 2. So once I have the structure of that, it makes it a little bit easier to fill in. So totally up to you if you want to do it as you plug in the numbers or set it up beforehand. Since we already established in the very beginning that our height was going to be 1 for all of these trapezoids or rectangles, we are going to just go ahead and fill in 1 for all of our heights. And so our next job is to figure out what bases to use for left and for right. And again, this is good practice on what we learned last time. So for your left RAM, remember that we do not use the last y value. So you can either cross it out momentarily, or I like to cover it up because I know I'm going to switch and do the RAM in just a minute. So if I'm not using the 10, the 3 bases that I am going to use are 1, 2, and 5. And then for right RAM, we know the shortcut switches so that we do not use the first y value, but the other 3 bases are what we need, so the 2, 5, and the 10. So now it's just a matter of doing the arithmetic. So when I added up my left RAM, I got an 8. My right RAM was a 17. Still got to add those together and divide by 2. So that gave me 25 over 2, which would be the same as 12.5. I just wanted to make a comment about the structure of this. This format is not something that you prefer. There's a lot of ways to express the same concept. You can factor out the 1/2. You can figure out L and R RAM separately and then add them together and divide by 2. As long as you end up at the same place, that's what matters. The final answer should be 25 over 2. So kind of play around with that. If there's a better way for you to think about it and set it up, that's fine with me. So let's fill in this answer about the over-under estimate. And for this particular one, we have a graph to look at since we have the x squared plus 1 in front of us. And I see that that graph is concave up, and I know that's what determines the difference between the over and under for trapezoid. So if I have a concave up graph, I'm just going to do a little sketch. Even though I'm looking at the graph in front of me, it still helps me process. If you connect your trapezoid, draw the bases, I can see that my trapezoid goes over my concave up function, so it's an overestimate. So just as we had for rectangular, we have some shortcuts that we can use, and this first one's actually the same. It does only work if your subintervals have equal length, but it's that h equals b minus a over n. And you might have noticed that when you did your L and R RAM, your first and last functions values, so your 1 and your 10, were only used once, but all the other y values were used twice. So So that's just something interesting to know.